Hello everyone and welcome to my channel. Today I'm going to talk about the topic of weak bases in relationship with the pKa and the pH. I uploaded a video about weak acid, pH and pKa. If you want to watch that first and come back and watch this one. So it's going to be the same principle but slightly different. I'm going to be using my tablet to talk about the different scenarios. And from there we go. pH in relationship with pKa with weak acid, we have a different formula. It's slightly different from the acid formula. So it's going to be pH equal pKa plus log. For the base, it's going to be the log of the non-ionized over the ionized. So if you remember, for the weak acid, it was the portion of the ionized over the non-ionized, but for the base, it's the portion of the non-ionized over the ionized. So here it's going to be the same principle. Basics works better in an alkaline environment and acid works better in an acidic environment. So for the purpose of this video, we're going to just talk about weak bases. So let's do some clinical question. At what pH will each of the local anesthetic agent exist at 50% ionized and 50% non-ionized? Just a word, all the local anesthetic are weak bases. And when the pH is equal to pKa, pH is equal to pKa, we're going to have them 50% ionized and 50% non-ionized. Second question, inflamed tissue has a lower pH when compared to non-inflamed tissue. What will happen to the speed, onset, and the efficacy of local anesthetic agent when they are injected into inflamed tissue, and why? So, because local anesthetic are base and they work better in an alkaline environment, they're gonna work better the ionized portion, the non-ionized portion. So when we give bases to an inflamed tissue which is acidotic, they will not work better. So the speed of reaction and the efficacy is gonna be much more lower. The other question is, what will happen to the speed action of each local anesthetic agent when administered to an alkalotic patient? 7.5. They work better in an alkaline environment, so the speed and efficacy is going to be higher and faster. What will happen to the speed onset of each local anesthetic agent if sodium bicarbonate is added to the agent in the drug preparation, and why? The speed, because sodium bicarb is a base. Remember, when a patient is acidotic, we tend to give them sodium bicarb drip because it's a base. So bases work better in a basic environment. So the speed onset and the action is going to be faster. Now, which of the following agent, we are giving multiple agent and we want to know which one is going to be more ionized than the other. So let's list our agent. We have lidocaine with a pK of 7.9, cocaine with a pK of 8.7, cocaine with a pK of 8.9, mepivacaine with a pK of 7.6, and we have our physiological pH 7.4. So we want to know we want to know the greater fraction of a drug that is going to be existing in the ionized form and non-ionized form. So if I draw my pH 9 here, 14, 0, acidotic, alkalotic, and I have it physiological here. And I have mepivacane 7.6. I have lidocaine 7.9. I have cocaine 8.7. And I have procaine 8.9. Now, which one is going to work better? Remember, we are talking about bases. Bases work better in alkaline environment, and bases are more ionized below the pH. So this is another concept that tied up together into answering all these questions. We need to be able to remember that bases work better in alkaline environment, and bases are more ionized below the pH. So I have my pH at 7.4, and I have listed all my weak bases as local anesthetic. So the more the base is going to be below the pH, the more it's going to be in ionized portion. So here 8.9, which is the procaine, is going to be more ionized because it's the one that is lowest. Bases are more ionized below the pH, and mepivacane is going to be less ionized because it's not that lower. So mepivacane is going to have the speediest onset of action and more efficacy. Now let's go back to another question. We are given midazolam with a pKa of 6.2. Midazolam. So midazolam has a pKa of 6.2. The parental preparation of midazolam is buffered in a solution that has a pH of 3.5. So the solution is 3.5, allowing the drug to be water soluble. So this environment allow midazolam to be water soluble. After administration to the patient who has a pH of 7.4 pH, 90% of midazolam exists in a non-ionized form. So midazolam is going to exist in a non-ionized form, and we are asked to know, is midazolam a weak acid or a weak base? So we're going back and remembering the concept. Bases work better in an alkaline environment. So if a drug is in an alkaline environment and it is in the non-ionized form, which is the active portion of the drug, then we should know that this is a base. And this is the acid environment. Midazolam was water soluble, so it couldn't work better because it's going to be easily excreted by the kidneys. So from this concept, bases work better in an alkaline environment, we know that midazolam is going to be a weak base. So now we have a problem from question 8 to 10. I'm going to wipe the board. question talked about use the following information from 8 to 10. Etomidate is a weak base. We are given the base. Hypnotic agent that is used for the induction of anesthesia and has a pKa of 4.2. Etomidate has a pKa of 4.2. Etomidate is available in 10 ml and 20 ml vials that has been buffered at a pH of 6. pH of 6. What happened to the degree of ionization of etomidate as the pH of the environment is increasingly becoming more alkaline? So we were given that etomidate is a weak base and the environment is becoming more alkaline, and we know that acid works better, bases work better. Bases work better in alkaline environment. So if the pH is going up, alkaline, so our etomidate is going to be more in the non-ionization form. Second question, the usual recommended dose of etomidate for induction of anesthesia is 0.3. So the dose is 0.3 milligram per kg, and the weight is 80 kg. Etomidate is supplied in a vial of 20 ml. One vial equals 20 ml with a concentration at 20 milligram for 10 ml. How many total milligram of etomidate in one vial? So total milligram. One vial has 20 ml, and we are given that the concentration in 10 ml is 20 milligram. So in 10 ml, I have 20 milligram. So to get the one vial of 20 ml, I will just have to multiply by 2 and I'll have 40 milligram. So the total dose of etomidate in milligram is going to be 40. We are asked, and what will be the correct dose in ml to administer to the patient? So the dose for this patient is going to be 0.3 milligram times 80 kg, which give us 24 milligram. But we want it in liter. The question wants it in liter. And we know that 20 milligram give us 10 ml. 24 milligram will give us 12 ml. So this is just like in nursing school when we were doing the heparin calculation. Is much better. Now at physiologic pH equals 7.4, etomidate exists predominantly in the ionized or the non-ionized state. So if we have a pH 7.4 and pKa of 4.2, the pH is greater than etomidate pKa, and this is a base. So we are in an alkaline environment, and bases are works better in alkaline environment. So etomidate is going to exist in the non-ionized portion, the more. Now, what is the fraction of etomidate that exists in the ionized and non-ionized preparation of the drug? Now we got, because they are asking us about the fraction, so we got to plug in the variable into the formula. So pH 7.4 equal the pK 4.2 plus log of the non-ionized midazolam over the ionized midazolam. So log of the proportion equal 3.2. I'm just moving 4.2 right here. And the proportion of the non-ionized over 10, 3.2 equal 1585 over 1. So this is our proportion. The non-ionized over the ionized. So we have more non-ionized than deionized. We have 1585 more non-ionized than the ionized portion of the drug. And this confirms what we said earlier, weak bases work better in alkaline environment. So we want to bring this now to the percentage so we can find a solution to the question. So because this is a proportion, technically 1585 plus 1 gives us 100% of the drug. Now, how many percent 1585 will give me? So if I plug in the variable, 1885 will give me 1585 times 100 over 1585 plus 1, which is gonna give me 99.9%. So 99.9% is gonna be non-ionized form, and the ionized form is gonna be 0.1%. So as the pH is increasing to an alkaline environment, our weak base is gonna be working better, and we have more non-ionized portion of the drug. Now the last question: at a pH of 7.4, which medication will have the higher percent in ionized and non-ionized between etomidate and procainamide? Now we have a pH here 14, 0, and we are giving 7.4. So etomidate has a pKa of 4.2. 4.2 etomidate, and procainamide, I gotta look back for his pKa. Procaine has a pKa of 8.9. 8.9 procaine. So we are asked to know are these so if we have a patient that has a pH of 7.4, Which medication will have the highest fraction in non-ionized state? Etonamide or procainamide? So for this question, it's going to be the same as we always did. Bases work better in an alkaline environment, and acid works better in acidic environment, and both of them are bases. I am not going to answer this question. I want to make sure that you guys understand. If you find the answer to the question, put on the comment below and I'll be answering. Thank you. You can subscribe, like, and share, and that will help me. Thanks.